Usually when we look at a physical object, like a massive steel suspension bridge or even a car engine, we tend to think of it as something entirely static.
Right, yeah, it's just a fixed artifact.
Exactly. It's forged, it's bolted together, and it's done. There's this
Yeah.
comforting permanence to it, right? It just sits there and does its physical job, weathering the elements until it eventually needs replacing.
Yeah, traditionally, a physical structure operates exactly as it was built to operate on day one. I mean,
Yeah.
nothing more and nothing less.
But then you step into the reality of modern engineering, and suddenly that static bridge is, well, it's feeling things.
Oh, absolutely. It's sensing its environment.
Yeah. It's actively sensing the weight of the morning traffic. It's adjusting its load-bearing profile in response to heavy winds. And that car is, learning the layout of the physical roads you drive every day.
And optimizing its battery chemistry on the fly to get you home.
Right. We're moving from a world of static objects to a world of living, adapting blueprints.
And that shift, it fundamentally changes our relationship with the built environment. We are no longer just building tools. We are building systems that participate in their own ongoing design.
Today, we are looking at the blueprint for this new world. We've got our hands on a really fascinating 2025 text by Kevin Kai called The AI-Enabled Engineer, a comprehensive framework for engineering excellence in the age of intelligence.
It's a fantastic read.
It really is.
Yeah.
And our mission today is to figure out exactly how algorithmic intelligence is breathing life into physical steel. The core concept here is intelligence plus crafting.
Meaning engineering is no longer just about bending metal in a factory.
Or writing code in a dark server room. It's about fusing those two disciplines together. And whether you are a tech enthusiast, a manager making strategic decisions, or just someone who uses a smartphone, understanding how these integrated systems are designed gives you a cheat sheet to the future of technology.
Because you are the end user of all this.
Exactly.
Yeah.
But to really grasp the magnitude of this shift, we need to clarify the technological era we are actually operating in right now, don't we?
We do. And the text makes a very sharp distinction here that honestly clears up a lot of the confusion we see in the media.
Right, the whole AI is taking over narrative.
Yeah, exactly. We are currently transitioning out of the information era, which was, dominated by the internet, massive data accumulation, and humans manually processing that information.
And we are entering what the book calls the age of intelligence.
Yes. Which is distinctly different from the future AI era.
Distinctly different.
Right. The hypothesized AI era implies a future state characterized by artificial general intelligence, where autonomous systems might make independent economic, social, or physical decisions.
Well, we aren't there yet.
We aren't. Today, in the age of intelligence, AI is an embedded tool. It's a highly advanced adaptive component that augments human capabilities. It processes complexity at a scale we can't, but it absolutely serves human-directed goals.
Okay, let's unpack this. Because to understand how this embedded AI is changing the way things are built, we first have to look at the foundational DNA of how engineers actually think.
How they solve problems, basically.
Right. The source breaks this down into a hierarchy, principles, methods, and approaches.
Yeah, that hierarchy is the structural pillar of the entire engineering mindset. At the very base, you have principles.
Which are the fundamental truths.
Right. Exactly. They represent the why. They are unchanging truths grounded in the laws of physics, thermodynamics, and pure logic. Gravity, the speed of light, the conservation of energy.
Stuff that doesn't care if you have a faster computer.
Precisely. The physics of building a Roman aqueduct are the exact same physics used to build a modern hydroelectric dam.
Okay, so that's the base. What's next?
Moving up one tier, we find methods. Methods represent the how. These are the actual procedures and tools engineers use to accomplish a task.
Like math and testing.
Right. Mathematical calculations, experimental testing, physical observation, and then finally at the top you have approaches.
The overarching strategy.
Exactly. The framework that dictates how you weave multiple different methods together to solve a complex real-world challenge.
I want to try an analogy here to see if I'm visualizing this correctly. Let's think about cooking.
Okay, I like cooking.
So the principles would be the fundamental chemistry of heat and ingredients, right? How yeast makes dough rise or how sugar caramelizes. That chemistry never changes.
Right, that's just physics and chemistry.
Then the methods are your tools, your chopping techniques, your measuring cups, your oven.
And the approaches.
The approaches would be the full recipe you execute to bake a cake. So the tools, the methods, might upgrade from a hand whisk to a high-end food processor. But the underlying chemistry, the principles, remains absolutely identical.
That is a perfect analogy. While principles remain constant, our methods are evolving rapidly right now thanks to AI.
Because we are upgrading our tools.
Exactly. And since methods are the tools evolving the fastest, we really need to dive into the most fundamental method of all, which is math.
But engineering math isn't just sitting at a chalkboard, solving for x in a vacuum.
Right.
I mean, reality is messy.
Very messy, which is why engineers rely on two different mathematical categories, analytical and numerical.
Okay, break that down for me. Analytical is the exact stuff.
Right. Analytical methods are what most of us encountered in high school calculus. They provide exact theoretical solutions.
But only for simple problems.
Exactly. They are perfectly precise, but they are generally only solvable for relatively simple, idealized scenarios.
Because the real world has friction and wind resistance and unpredictable human behavior.
Right. So when a physical problem becomes too complex for an elegant analytical equation, engineers pivot to numerical methods.
Which means breaking things apart.
Yes. Taking an impossibly complex geometry, let's say, the wildly curved surface of a commercial airplane wing, and discretizing it, slicing it into millions of tiny, manageable geometric shapes like little triangles.
And then the computer solves the math for each tiny triangle.
Exactly. And stitches those millions of tiny solutions back together to understand how the entire wing will behave in the air.
This was a really surprising takeaway from the text for me. Engineering isn't always about being exactly perfect. It's the art of approximation. It's about being practically perfect.
And the impact of that mathematical approximation on our daily lives is profound. Think about the smartphone in your pocket.
Which relies on cellular networks.
Right. To make those work, engineers have to model how electromagnetic radio waves propagate through the air, bounce off glass skyscrapers, penetrate concrete walls.
And interact with the silicon inside your phone. There's no single perfect equation for all of that bouncing.
It's mathematically impossible. So engineers utilize a tool called Green's function, which calculates a system's response to a single impulse.
But they don't look for a perfect analytical solution.
No, they use numerical approximations of Green's function. The AI models these millions of bouncing waves just accurately enough to optimize the antenna design. It allows you to seamlessly stream a video while riding a subway.
The source also dives into Six Sigma in this context, which was wild to me. I always assumed Six Sigma was just corporate management jargon.
A lot of people do, but it's actually a statistical approximation method for physical quality control.
Because absolute perfection in manufacturing is a myth.
Exactly. If a factory is cutting 1 million steel bolts, the machinery will have microscopic variances, the blade wears down, the room temperature shifts.
So instead of chasing impossible perfection, Six Sigma aims for 99.99966% perfection.
Which is exactly 3.4 defects per million opportunities.
That is just a wild number. But let me push back on this for a second. Is approximation just a sanitized word for a highly educated guess?
Not at all.
Does this mean the suspension bridges we drive over and the phones we use are built on calculations that are simply good enough?
What's fascinating here is that approximation isn't guessing, it's calculated tolerance.
Meaning they know exactly how wrong they can be.
Precisely. Engineers mathematically define the exact threshold of error that can exist before safety is compromised, and then they build massive safety multipliers on top of that.
And AI helps with this.
Massively. AI is heavily used now to search vast historical databases of stress tests and suggest the absolute best approximation strategies instantly.
Wow. Okay, so you map out the math, and the AI helps you find the optimal approximation. But eventually, you can't just math your way to a physical product.
No, you definitely cannot.
You have to subject it to reality. Which brings us to experimental and observational methods.
Right. Once you have that mathematical approximation, you have to validate it. The text outlines 6 levels of experimentation, moving from simple observation all the way to full system validation.
And the historical examples in the source are so cool here.
Yeah.
Like the Faraday cage.
Oh, yeah. Born purely out of basic observation.
Exactly. Michael Faraday just carefully observing electromagnetism.
Yeah.
Or Wilhelm Röntgen discovering X-rays through systematic trial and error with cathode rays.
Manipulating the physical conditions until he understood the mechanism.
Right. But today, those foundational observations scale into more complex methods, like progressive staging.
And the iPhone is the perfect modern example of this.
Yeah. Apple didn't sit in a lab in 2007 and try to invent the iPhone 15 with LiDAR scanners and neural engines.
No, they staged it. They built a basic multi-touch screen, validated it, and then progressively built on that foundation, targeting specific new goals with each generation.
It's incredibly similar to biological evolution, honestly.
How so?
Well, a complex organism doesn't just appear out of nowhere. It evolves step by step from a simpler predecessor. Each stage builds on the successes of the last one.
That's a really great way to look at it. But there is a huge difference today thanks to digital tools.
Which is what?
Simultaneous operation. Modern engineers don't do these steps one by one anymore.
Wait, really? They run them at the same time?
Yes. They run level A, which is basic observation, and level D, which is full system integration, simultaneously for faster
It's
iteration.
using digital twins, right?
Yeah. Exactly. They observe a physical material breaking in a lab while simultaneously running a virtual simulation of the fully integrated jet engine inside a computer.
That is mind-blowing.
hmm
But once you've tested all the individual parts, you face the ultimate modern engineering challenge.
Making them all talk to each other.
Right, which is the realm of system methods. And the text notes 8 properties of systems, basically highlighting how incredibly complex they are.
Cause and effect, deep interconnectedness, feedback loops.
Right. And the examples of how different engineering fields handle these systems are just fascinating. Let's look at mechanical engineering.
Robotic assembly lines are a great example here.
Yeah, these aren't just dumb machines pushing a screw until it strips. These robotic arms use force feedback sensors to dynamically adjust their grip in real time.
If they detect an anomaly, like a slight resistance, the electrical current spikes, and they instantly adjust.
And civil engineering is doing the exact same thing with smart bridges.
Equipped with continuous fiber optic strain gauges and computer vision.
It's wild. They embed glass cables in the concrete, and if the bridge bends under heavy traffic, the cables bend, altering the light traveling through them.
So the bridge can actively monitor its own structural health.
Right. And if an earthquake hits, it adjusts traffic signals automatically. Then you have electrical engineering handling EV charging networks.
Balancing grid stability with the vehicle's demands using protocols like CCS or CHAdeMO.
It's just so much data. Which brings us back to AI as the hub.
Yes, the hybridization of methods. In the past, engineers relied on observational or mathematical methods depending on the era.
But today,
Today, AI acts as a central integration hub. It allows engineers to blend all these methods simultaneously.
but wait, if AI is acting as the central hub, modeling the math, monitoring the smart bridges, isn't the AI essentially becoming the engineer?
That is the big question, but the text is very clear on its stance here.
Oh.
AI is a powerful tool for synthesis, but it requires human judgment.
To validate the methods.
Exactly, and to ensure the ultimate principle of no harm to humans. The book actually references Asimov's 3 laws of robotics here.
Right. A robot may not injure a human being.
The AI can optimize the bridge traffic, but a human engineer has to decide the acceptable level of risk for human life.
Okay, so if the AI is handling the heavy integration and computation, what is the human engineer's primary job?
It all comes back to the very foundation of the hierarchy we discussed at the start.
Principles.
Specifically, first principles thinking, breaking a problem down to its most fundamental, irreducible elements.
Like physics or computational limits.
Right, rather than relying on analogies or past designs.
And the book uses Elon Musk and Tesla as a fantastic example of this.
Instead of asking, how do we put batteries in a gas car?
They used first principles to ask, what are the fundamental components of an electric vehicle? Which led to using the battery pack as a structural element of the car itself.
And treating the car primarily as a software device.
Which is brilliant.
Yeah.
But to pull that off across massive global teams, you need a way to document the thinking.
Which introduces chain of thought, or COTI.
Right, from that 2022 Google paper by Wei and colleagues.
Yes, Wei et al. Chain of thought is a method of explicitly documenting the reasoning process step by step.
So COTI is essentially like your high school math teacher forcing you to show your work, but applied to billion-dollar integrated systems.
If we connect this to the bigger picture,
Yeah.
that is exactly what it is, and it's vital today.
Because of the massive global teams.
Right. When you are building safety-critical systems, showing your work allows for rapid error detection, knowledge transfer, and algorithmic transparency. We can't afford black box engineering where we don't understand how the AI reached a conclusion.
We really can't. Well, we have covered some incredible ground today.
We definitely have.
Let's summarize this for everyone listening. We've journeyed from the complex math that makes your cell phone work, to the smart bridges you drive over, all the way to the foundational first principles thinking that builds an electric vehicle.
And AI is the ultimate tool weaving all of these physical and digital methods together.
Exactly. But why does this matter to you, the listener? Well, because you are the end user of these integrated systems.
You interact with them every single day.
Right. Understanding that your world is built on intelligence plus crafting helps you navigate this new age of intelligence, whether you're evaluating a new piece of tech at work or just applying first principles to your own life and career.
It demystifies the magic and shows you the actual nuts and bolts.
It really does. But I want to leave you with one final, slightly provocative thought to chew on.
Oh, let's hear it.
We just established that first principles thinking requires breaking problems down to fundamental truths that humans have discovered through centuries of physics and math.
Right, our bedrock.
But what happens when AI systems become advanced enough to discover new fundamental truths of physics? Truths about the universe that human brains literally cannot comprehend.
Wow, yeah.
If the AI starts operating on physical principles we don't understand, who leads the engineering process then?
That is the million-dollar question for the dawn of the true AI era.
Something to mull over the next time you drive across a smart bridge. Thank you so much for joining us on this deep dive. Stay insanely curious, and we'll catch you next time.